Yellow learners, yellow grade 12s, welcome to Edge Blush Virtual Academy. Thank you so much for joining your presenter. And your presenter is Mr. Sylvester. Taking you through physical science. It is always a pleasure to have you guys following our lessons, our presentation. All right. We are still looking at a very beautiful topic, very interesting. We are looking at work energy and power. And I've presented 7 previous presentations trying to explain how to calculate work done and how to draw free body diagrams, how to calculate network done, as well as how to apply the work energy theorem. Just a recap, some of the things that we need to catch up with, some information from the previous presentations that is very critical and very important to us. Um, I gave you 3 options that we can use to determine or to calculate network done. If you check my previous presentations, presentation number 6 and presentation number 7, you get this information that I'm giving you now. I said there are 3 options that you can use at this level to calculate network done. Number 1, when you are given a scenario of an object with forces acting or exerted on the object, you can calculate work done by each force and then you add them together because net we are summing up forces. So when it's net work done, we are summing up work done by all the forces. But as you calculate work done by each force, you must always bear in mind, you must always appreciate that all the perpendicular forces, and when we say perpendicular forces, those are the forces will be acting on the object but at an angle of 90 degrees. So when those forces do no work because their theta or their angle of the force and the direction of motion is 90 degrees and cos 90 gives you a 0. So you calculate work done excluding perpendicular forces, then you add them together and that's how you get your network done. That was option number 1. Option number 2, boys and girls, you can also use Fnet. Wnet or network done is equals to Fnet multiplied by the displacement multiplied by cos theta. Your theta will be the angle between your Fnet and your direction of motion. But how do we calculate Fnet? We need to sum up or to add all the forces that are parallel to motion. But as we add up all the forces parallel to motion, we must always bear in mind that force is a vector quantity and therefore direction matters. So we calculate our F net by displacement by cos theta, and then we get our W net. But as we calculate F net, I always encourage my learners to take the direction of motion as positive. Right. So another method that we use for calculating W net, it is the work energy theorem. Now, what is this work energy theorem? We discovered that the network done on a particular object as it moves from point A to point B, it is equivalent to the change in the kinetic energy of that particular object. So how do we calculate the change in kinetic energy of the object? It is final kinetic energy minus initial kinetic energy. So we have looked at that, which is the work energy theorem. You must also know how to state the work energy theorem. Now, as we come to the towards the end of our topic, we are introducing work done by non-conservative forces, and that is going to be the lesson for today. So we need to know the definition. It's according to the examination guideline of our CAPE syllabus. You need to know the definition of a conservative force, the definition of non-conservative force, examples of conservative forces, examples of non-conservative forces, and then how to use the formula for non-conservative forces. And then I've done one example for you, and I'm going to upload an activity for you in the next presentation so that you can try, you can attempt to do the calculation using work done by non-conservative forces. Right. Before I can switch off the video so that I can be writing something there, um, I want to give you a definition of a conservative force, and I'll try to generalize it and try to explain a bit. Remember, we are looking at a closed path. And when we say closed path, we are saying the object will travel, will move, and come back to the same point. That is a closed path. So it's more like you are throwing an object up and it comes back to your hand to the level where you started. That pathway is called a closed path. So we are saying conservative forces, to conserve something is to save something, right? That is to conserve, to keep something constant. That is to conserve. So what is the proper definition of these conservative forces? Remember, friends, okay, undergrade 11 in our syllabus, when we're looking at forces under vectors, remember we realized that there are so many ways we can use to classify or to categorize these forces. Forces can be classified as internal, external. Forces can be classified as contact, non-contact. Those are different ways of classifying forces. And under work done, we are saying we can classify our forces as either conservative forces and non-conservative forces. I think it's contextual in the sense that conservative forces, the explanation goes back to work done. How can we classify our forces with relation to what we have been talking about, which is work done and energy changes in a system? All right. So when you talk about conservative forces, at the back of your mind, something must click in, which has to do with something being kept constant or something remaining constant. So conservative forces, I'll write the definition for you. I just want to explain first before I start writing. So conservative forces, um, a force is a conservative force if the network done by the force to move the object along a closed path that starts and ends at the same point is zero. So, like I said, um, conservative forces, they are also known as non-wasteful or internal forces. So it means if we take, for example, a good example of a conservative force that we have is gravitational force. We take an object that is thrown up to a certain height and it comes back to the same level. We calculate our work done by gravitational force as it goes up and gravitational force as it comes down. Um, you realize that the network done by gravitational force will be equals to zero. Why are we getting a zero, especially in the case of gravitational force? When the object is going up, Fg is going down, is doing negative work. So you are going to get a negative work done. When the object is coming down now, it's going in the same direction with gravitational force. So you realize that you get a positive work done. All right. So the two work done, they will cancel each other. So in other words, we are saying work done by conservative force, there is no change in energy because the net work done is zero. Going up is negative, coming down it's positive. Negative and the positive, they cancel out because the magnitude of the work done is the same because you're talking of the same object, right? So this is a conservative force because the net work done is zero. So in other words, there is no change in energy. So when we say equals to energy transferred, right? So the energy can be transferred to the object or the energy can be transferred from the object. But when we calculate work done by a conservative force in a closed path, we realize that the network done is zero, which means there is no change in energy. So our energy has been conserved. So this is where the term conservative comes in. So it means our energy has been conserved. So the network done is zero. There's no change in energy. Right. So examples of conservative forces that we have is gravitational force. Right. We move on to the next definition, non-conservative force. It means something is not saved there. Right. So non-conservative forces, we can also call them wasteful or external forces. They are wasteful because they don't conserve something here. Right. And remember, we are defining this in context of work done. So a force is a non-conservative force if the net work done by the force to move the object along a closed path that starts and ends at the same point is not zero. So we are saying, let's look at a very basic example of a non-conservative force that we are going to deal with is frictional force. Let's say an object has moved from point A to B and from point B back to point A. If you calculate work done from point A to B, you get a negative answer, right? You calculate work done by friction from point B back to point A, you still get a negative work done because your theta is always 180, right? So you are going to get negative work plus negative work. So you sum up the two, they don't cancel out, right? So it means the net work done by a non-conservative force is not zero. You see that we are defining our forces in context of work done. So here we are saying energy has been transferred. The fact that we have got negative and net work done, it means energy has been taken away from the object. So there is energy that has been transferred. So energy has not been kept what? Has not been kept constant. So the net work done by a non-conservative force depends on the path taken. Right. So the work done by non-conservative force depends on the path taken. So the work done by friction depends on how far the object is going. The further you move, the greater the work done. So it means energy is not conserved, is not kept constant. So the work done by non-conservative forces acting on an object is equal to the object's change in mechanical energy. So through calculations, we can just to cut the long story short, it is discovered that the work done by non-conservative force, let's say the work done by frictional force, let's say an object is sliding down an incline, it has been noted that the work done by non-conservative force, which is friction, is equivalent to the change in mechanical energy. But we know that mechanical energy is the summation of EK plus EP. So in other words, work done by non-conservative force will be equals to the change in kinetic energy of the object plus the change in gravitational potential energy of the object. That's the method that we are going to use. That's the formula that we are going to be using in our example. And then we are done with our beautiful presentation. Right. Um, so I'm going to write the definitions for you. Um, I'm going to write the definitions for you now, and you are going to be following all the definitions. Like I've already explained these definitions, so it's just a matter of you guys getting notes on these definitions, and then I do an example for you. So let's start with conservative force. What are these conservative forces? So conservative forces. So in bracket, you can write FC, right? You can write FC. That is as a conservative what? The conservative force, right? By definition, conservative forces, we are saying a force is a conservative force. A force is a conservative force if the network done, if the network done by the force, if the network done by the force to move, right, to move the object, to move the object along a closed path. I think we need, friends, to underline the term closed path that starts and ends at the same point. That starts and ends at the same point. That's a closed path. It starts and ends at the same point is zero. So we are saying the network done by a conservative force is zero, which means our energy, mechanical energy, has been what? Conserved. And the most common example of a conservative force that you guys must know that we are going to be using is gravitational force. And take note, they love this gravitational force so much. They always ask you in exam, what is the name of the conservative force that is acting on the object? You realize that it is gravitational force. The network done by this force in a closed path is zero. In other words, our energy is conserved. So it is called conservative because it conserves energy, because network done is zero. There is no energy that is transferred. Then the second one, it is non-conservative force. Non-conservative force. We can call it FNC like that, which is a subscript, right? So what is a non-conservative force? The definition says a force is a non-conservative. A force is a non-conservative force if the net, right? If the network done, if the network done by the force, if the network done by the force to move the object along a closed path, along a closed path, or a path that is closed, right? I'm sorry for that grammatically. A path that is closed, in other words, that starts and ends at the same point. At the same point is not zero. So we are saying work done by non-conservative force, the network done is not zero. In other words, energy is not conserved. That is the bottom line. Energy is not conserved. It's going to be transferred, right? So, in other words, if we want another definition, maybe just for interest sake, we can say the work done. Remember, we said we are defining this in context of work done. So, the work done by a non, the work done by a non-conservative, the work done by a non-conservative force depends, right? Depends on the path taken. Like I said, frictional force is a very good example of a non-conservative force. And if an object is pulled from point X to point Y, right, the work done by friction will depend on how far is it from point X to point Y, right? So the further the object is moved, the bigger the work done. So in other words, the work done by non-conservative force depends on the path that is taken. All right. The examples of non-conservative forces, let me say e.g. examples. The most common one is the frictional force, right? And then we have also air resistance, right? Then we have got also tension in a rope. Let me just say tension. And then we also have got applied forces, that is push or pull forces. So normally these are applied forces. So when we talk about non-conservative forces, we are talking about forces whereby their network done on an object in a closed path is not zero. In other words, energy is not conserved. That's why they are called non-conservative. They are wasteful. Energy is lost. Energy changes when a non-conservative force is doing work on a particular object in a closed path. Right. So the next slide that we are moving to, we are deriving our formula now, the most interesting and one of the longest formula that we use under this topic. So the next bullet that I'm going to write, it says the work done, it says the work done by non-conservative, the work done by non-conservative forces acting on an object, acting on an object is equal, very interesting, is equal to the object, is equal to the object's change in its mechanical energy, in mechanical, underline the term, a mechanical energy, right? So in other words, we are saying symbolically, Work done by non-conservative force will be equivalent to the change in the mechanical energy of an object. But we know that mechanical energy is the summation of kinetic energy and gravitational potential energy. So if it's change in E in M, then it means it has to be change in kinetic energy plus change in gravitational potential energy. That gives us the change in mechanical energy. So we can further expand our formula and say work done by non-conservative force is equals to change in kinetic energy plus change in gravitational potential energy. We can further expand the formula and say work done by non-conservative force is equals to, how do we calculate change in kinetic energy? EKF minus initial kinetic energy plus, how do we calculate change in gravitational potential energy? It's EPF minus EPI. Remember, when we calculate change in one variable in science, when we use delta, it's always final minus initial. Please. We further expand our formula. Work done by non-conservative force is equals to, how do we calculate final kinetic energy? Half mv squared F minus half mv squared I. That gives us change in kinetic energy. Plus, how do we calculate final gravitational potential energy? It's mghf, right? Minus mgh initial. That gives us our work done by non-conservative. So if you are presented with a question or a scenario and you want to use this method, you must identify all the non-conservative forces that are acting on that particular object. So I'm going to look at an example, and in this example, the advantage is we have only one non-conservative force that is acting on this guy who is sliding down an incline. So since we have got only friction, it means our work done by non-conservative forces is going to be equivalent to work done by friction because it is only friction that is a non-conservative force. So quickly, let me look at the example and then I revise the example with you. I revise the example with you. The example says here a, a 58 kg um, learner, a 58 kg, a 58 kg learner, right? This must be a heavy learner. Ne? Learner slides down a 25 degrees slope, right? With an initial velocity of 3.6 meters per second, right? Over a distance, right? Over a distance of 57 meters. A kinetic friction, because is in motion, right? A kinetic friction force of 70 newtons resists the movement. Resists the movement. Let us remember that kinetic energy friction always opposes motion. Then item A, calculate the gravitational potential energy. We are not going to draw a free body diagram here. Calculate the gravitational potential energy, right? Calculate the gravitational potential energy of the learner, of the learner at the highest point, at the highest point, right, of the slope, at the highest point of the slope. This one is very simple. The next one, which is actually the final one, calculate the speed, right, of the learner I believe this is a point of the learner at the bottom, all right, at the bottom of the slope. In other words, when the learner reaches the bottom part. And allow me to divide this page into two so that my calculation can fit. So you can actually have a sketch of the diagram here, a sketch of what is happening. You can have that bonus. So we are having something of this nature. Uh, Good. So this is the height, right? And then from here to here, they said, the examiner said it's 57 meters, right? And this angle is 25 degrees, right? So the learner is sliding on that incline. I'm not going to draw the learner there, but we can all appreciate uh, the slope and the learner going down, right? So we're having something like that. That is what we have. Now, where do we start? What is the first question? Calculate the gravitational potential energy of the learner at the highest point of the slope. But we have a problem here because our formula says EP is equals to mgh, but we don't have height. But we can see that this is a right angle triangle. Can you see that? So we have got hypotenuse, we have got our angle theta, so we can easily get our opposite side using our trig ratios, which is SOHCAHTOA. So we can quickly calculate the height separately, right? You can quickly calculate the height separately. So how do we calculate it? We use our sine, right? So in other words, sine theta, which is sine 25 degrees, is equals to opposite over hypotenuse. So in other words, our opposite is the height over hypotenuse, which is 57, which is what we have been given. So cross multiplication, you realize that your h is 24,09 meters. So now we have got our height. So it means our EP is going to be much easier now. So EP is going to be, what is the mass of the learner? It's 58, right? Gravitational acceleration, which is 9,8, and our height is 24,09. So in other words, our gravitational potential energy is going to be, you need a calculator for that. You need a calculator to verify that. 58 times 9,8 times 24,09, right? 24,09. You get 13,692,76 joules. So this is the gravitational potential energy at the highest point of the learner. Right, we're done with the first one. Calculate the speed of the learner, item number B. Calculate the speed of the learner at the bottom of the slope. So if I am to draw a free body diagram, I will realize that I'm having normal force, I'm having gravitational, there's no force applied here, right? Otherwise, it was going to be our second non-conservative force. So we have got normal force here, which does no work, it's perpendicular. We have got FG, right, which is a conservative force. And then we have got friction, which is our non-conservative force. So we have decided to use the formula for non-conservative force, and I've noted that in this particular scenario, it's only friction, which is a non-conservative what? Which is a non-conservative force. So in other words, I write the formula, work done by non-conservative force is equals to delta EK plus delta EP, right? So work done by non-conservative force is equals to half mv squared F minus half mv squared I plus mghf minus mghi. Then you close, right? So work done by non-conservative force Let's try to substitute there. We are looking for speed at the bottom. So it means our VF there is going to be uh, the one that we are looking for, right? Yes. And our initial velocity, it is given, it is 3,6. Okay, I think we are moving together. Our initial point is going to be the top of the slope. Our final is going to be the bottom of the slope. That is our final, and that is what we are looking for. So work done by non-conservative force is equals to half times mass. What is the mass? 58 times final. That's what we are looking for. Minus half times 58 times our initial velocity is 3,6, and don't forget to square, plus, right? Our MGH, our final H is 0 at the ground. So that gives me 0. I am not going to calculate it because of space. Our H at the bottom is 0. So everything, it doesn't have gravitational potential energy. Our initial gravitational potential energy at the highest point, we have calculated it, is 13,692,76. I hope you are following, friends. So I'm trying to simplify the right hand side so that I can be able to calculate work done by non-conservative force, because my slide here is very small. So work done by non-conservative force is going to be, uh, what are we getting here? Um, we are going to get, let's say, 58 divided by 2. I get 29. So this one is going to give me 29 VF squared minus, okay, that is 3,6 squared. Sorry, 3,6 squared. I'm getting 12,96, right? Times 29, which is half of that. I'm getting 375. So this is minus 375,84, right? Um, minus 13692,76, right? Like that. So we can actually collect like terms there, just to save time. So work done by non-conservative force is going to be 29 VF squared. That gives me what? 375,84, right? Let me include that one, 13,692, right, comma 76, right. I'm getting minus 14,068, comma 6, right. But remember, my work done by non-conservative force, the non-conservative force that is acting here is friction, right? So I expand the left hand side now. I said I'm doing this separate because of space. So work done by non-conservative force. The non-conservative force, there is frictional force. So work done by friction is equivalent to friction by displacement by cos theta. This is all equals to 29 VF squared minus 140,68,6. Right. What is the size of my frictional force? It's given somewhere, 70 newtons times displacement 57 times cos 180, because this is friction. It opposes motion. It goes in the opposite. So our theta is 180. This is all equals to 29 VF squared minus 1468,6. So I can simplify the left hand side now. Cos 180 is minus 1, friends. So this is going to be 70 times 57 only, which is going to be minus 3990, like that, which is equals to 29 VF squared minus 1468,6. Collect like terms. I take that one to the other side. So in other words, 29 VF squared uh, is going to be equals to 14068,6, right, minus 3990, right? I'm getting 10078, 6 divide by 29, divide by 29, right? Square root sign. Then my VF is equals to meters per second. So I'm getting uh, square root of, okay, square root of 10078, comma 6 divide by 29. That gives me 18,64. So 18,64. So in other words, using this method, which is the work done by non-conservative force, you can actually see that what is important is for you to come up with a free body diagram, and then when you are done with the free body diagram, you identify the non-conservative forces. I've given you examples of non-conservative forces, and those are external forces, right? So when you determine your non-conservative forces, you calculate work done by non-conservative forces, and that will be equals to the change in the mechanical energy of the object as it moves from point A to point B. So, ladies and gentlemen, friends, this is the method for work done by non-conservative force, and we need to practice. We need to use it. We need to continuously use it so that we get used to it. Thank you so much. I'm also going to include or to attach an activity so that you guys can practice on how to use all the formulas that we have talked about so far, including this last one, which is work done by non-conservative forces. Thank you so much for joining us, and thank you so much for following our presentations. God bless you.